Yesterday we looked at a type of biotechnology known as genetic engineering. Right now we're going to look at another type of biotechnology called DNA profiling. And you have probably heard of this before. You may have heard it called DNA fingerprinting, gel electrophoresis, or even genetic screening. All of these techniques are essentially the same thing and involve analyzing and comparing DNA from different sources. And this technique has a lot of applications. For example, DNA analysis showed that this school teacher was actually related to this skeleton, who is 300 generations older than the man himself. This convicted murderer was proven to be innocent based on DNA evidence, and he was finally freed after 17 years of wrongful imprisonment. In the case of paternity issues, DNA profiling can be used to prove who is actually the biological father. And we can also use DNA profiling to diagnose genetic diseases. For example, we can see if people have a predisposition towards cancer, if they're going to develop Huntington's disease, Alzheimer's disease, sickle cell anemia, amongst others, by comparing DNA. A more recent example of this, a couple years ago, a local murder that occurred here in New Haven. DNA evidence was used to link the victim to the suspect, and that led to his arrest and trial. So let's take a close look at how DNA profiling is done using the example of a crime scene investigation. So the first thing that has to happen is that you need to isolate DNA from the crime scene. The next thing you do is make lots of copies of that DNA, known as DNA amplification. And then finally, you compare the DNA that you found at the crime scene to the DNA of your suspects. Right now, we're going to take a closer look at each of these three steps, and we're going to pay particular attention to this step. So in terms of isolating DNA from the crime scene, there's lots of sources where a police officer could gather DNA evidence. Bones, blood, various body fluids all can provide DNA evidence. Now, sometimes there isn't very much DNA evidence. So the next thing a scientist would do is amplify the DNA. And this is done using a machine known as PCR, which is short for polymerase chain reaction. It's an automated technique that makes many copies of the DNA very quickly. So once we've got all these copies of the DNA, we can finally compare them using a technique known as gel electrophoresis. In here you can see an actual gel electrophoresis chamber, and a scientist right now is loading DNA samples into the chamber so that they can be compared. So we're going to spend a few minutes right now looking in depth at how this process of gel electrophoresis can actually compare DNA from different people. So here's the overview. We take DNA fragments from different suspects, different people, and we load them into wells on the gel. Now the gel is connected to a power source. It's negative at the starting point, and it's positive at the ending point. Once you turn electricity on and run it through the gel, the electricity causes the DNA to move from the negative end to the positive end. This is because DNA is negatively charged, and as we all know, negatives repel. And at the end of running the gel, you will see different bands of DNA based on the size of the DNA. In general, the shorter the DNA sequence, the faster it goes. The longer the DNA sequence, the slower it goes. And we can then compare these DNA bands. This is what's known as a DNA fingerprint, although it's not really a fingerprint, it's actually the DNA sequences from different people. So let's break this step down. The first thing we had to do was get those fragments of DNA. So if we had DNA samples from person 1 and person 2, our two suspects, we would mix those DNA samples with a restriction enzyme. And I'm sure you remember from yesterday, a restriction enzyme cuts only at specific sequences. In this case, we're using a restriction enzyme that likes to cut between the G and C of GC. Now, because person 1 and person 2 have different DNA sequences, the restriction enzyme will actually cut person 1 DNA 3 times, giving us these 2 fragments. But the restriction enzyme will only cut person 2's DNA twice, giving us 1 fragment. And again, that's because 2 different people have different sequences of DNA, meaning when you mix that DNA with the restriction enzyme, you're going to get different sized fragments. So now that we've got different sized fragments, what do we do with them? Well, we're going to put them in the gel and run those fragments through the gel. And remember, person 1 had one big DNA fragment, person 2 had 2 smaller DNA fragments. So when we run them through the gel, suspect 1 is going to have one DNA band close to the beginning of the gel, and suspect 2 is going to have 2 smaller bands further along the gel. The reason that these are further along the gel is that they're smaller in size than suspect 1's DNA sample. Now let's take a look at what exactly is happening as those DNA fragments run through the gel. Again, the DNA fragments go into these little openings called wells. Once they're in the wells, we turn the power source on. Again, it's negatively charged at the beginning actually, and it's positively charged at the end. Because DNA is negative, it's attracted to the positive end of the gel, so it's going to move through the gel. The longer fragments are going to move more slowly. The shorter fragments will move more quickly. And so, at the end of running the gel, we get bands of DNA, and each band represents DNA of a particular length. These bands are the shortest, these bands are the longest. Now let's go even closer. If we were to look at the gel under a microscope, what we would see is tiny, tiny particles of gel. And between those particles are openings called pores. And the DNA, once electricity is applied, actually has to work its way through those openings. It's kind of like a maze or an obstacle course. And of course, a smaller DNA fragment is going to be able to squeeze through those holes between the gel much more quickly than a larger DNA fragment. So, at the end of running the gel, our small DNA fragments form this band. The large DNA fragments, who couldn't squeeze through quite as quickly, form this band. So, let's sum all that up. We had DNA from suspect 1 and suspect 2. We cut that DNA with the same restriction enzyme, but because suspect 1 and suspect 2 have different DNA sequences, we got different sized fragments. We put those fragments into a gel, and because of the different sizes, we got different DNA bands. So now, let's analyze the results and find out who the criminal actually is. Here we have the DNA from the crime scene. Here we've got suspect 1 and suspect 2's DNA. And then we also gather the victim and the officer DNA because we want to make sure that what we gathered at the crime scene wasn't from either the victim or the officers investigating. So if we compare the evidence DNA with our suspects, we can see that these two bands match up with suspect 2. So we could conclude that suspect 2 is the criminal. Now this was a bit of a simplification. In a real crime scene investigation, they actually compare 13 different restriction enzyme samples just to make sure that there is no statistic reason for a matchup. But the same principles apply. If you were an actual forensic scientist, you would just analyze more DNA. So, recap of the whole procedure. We collect the evidence from the crime scene. We isolate it and make more copies if we need to via PCR. We cut the DNA into fragments using restriction enzymes, and each person has a different size of fragments, unless of course you're identical twins. We run those fragments through a charged gel, a gel electrophoresis, and we get a banding pattern that allows us to analyze the results and deduce who the criminal likely is. And again, this procedure we looked at for a crime scene investigation, but we can do the same thing for a paternity test. We can do the same thing for analyzing a genetic disease. And in class tomorrow, you will get a chance to do some virtual simulations of this and conduct your own criminal investigations and paternity tests. If you didn't take notes over this, please go back through and make some notes of the important steps. Don't forget to complete the poll and complete any additional reading assigned.